Welcome back to the deep dive. For years, we've heard these promises, haven't we, about the future of electric vehicles.
Oh yeah, faster charging, lighter batteries.
And the big one, huge increases in range. But it always felt like, 5, maybe 10 years away.
Always on the horizon.
Well, today we're diving into some news that suggests that seemingly impossible benchmark may be, just maybe, doubling EV range. It might have just been shattered.
That's absolutely right. And the source for this really huge announcement is the Chinese automaker Chery.
Chery, okay.
Yeah, at their 2025 Global Innovation Conference in Wuhu, just on October 18th, they actually unveiled their first all-solid-state battery module prototype.
Wow. Okay.
We're talking technology that could potentially deliver over 1,300 kilometers on a single charge.
1,300.
Yeah, this isn't just like a small step. It's potentially a complete game changer for how people think about long-distance EV travel.
Okay, let's unpack this then, our mission today. Let's try to verify these, frankly, jaw-dropping technical claims. Look really closely at Chery's incredibly aggressive timeline for commercialization.
Right.
And then try to put this whole thing into context, the global battery race, the skepticism that always surrounds these solid-state battery prototypes.
Absolutely. There's a lot to dig into.
So let's start with those headline numbers from the conference. What exactly is the core technical achievement Chery's shouting about?
Okay, the key number, the big one, is the energy density they achieved at the cell level. It's 600 watt-hours per kilogram.
600 weight HK.
600 watt kilograms. And what's fascinating here is that immediately sets a new high water mark, certainly for any Chinese automaker that's announced something like this.
Right. And for perspective, what are we looking at today in production cars?
Well, the current highest end production batteries, they sort of top out around 300, maybe 350 wage kilograms if you're lucky.
So they're claiming almost double in a lab prototype, mind you.
Exactly, almost double. In the prototype stage, yes.
And for you, the listener, what does doubling that energy density actually mean when you're behind the wheel? What's the practical effect?
It means range anxiety could just evaporate. Theoretically, a sedan built with this kind of pack could maybe exceed 1,500 kilometers.
1,500, theoretical.
Theoretical.
Yeah.
Now, Chery was careful. They translated that theoretical number into a more real-world figure. They stated the effective driving range, even for bigger vehicles, high-energy consumption SUVs and the like, would not drop below 1,300 kilometers.
1,300 real-world kilometers. That is massive. But let me push back just a little bit on that comparison.
Okay.
When we talk about current high-end EVs maxing out around 500, maybe 600 kilometers, that's often based on EPA or WLTP tests, right? Which can be conservative.
Yep.
Some modern packs, under the best conditions, are already nudging towards 700, maybe 800 kilometers in the real world. So is Chery really doubling range, or are maybe comparing against slightly older benchmarks?
That's a really fair point. And yes, there are some outliers hitting that 700, 800 kilometer mark now. But I think the critical difference here is the weight needed to get that range. Those long-range liquid-ion packs, they are enormous. They're heavy. The real power of 600 weight drums is you could achieve that 1,300 kilometers with a much lighter, maybe smaller battery pack.
Or flip side, get current ranges with a tiny super light pack.
Exactly. That density itself is the strategic breakthrough. Kind of regardless of the precise percentage increase over the absolute best battery today, it changes the design possibilities.
Understood. Okay. So how did the Chery Solid State Battery Institute actually pull this off? We know they're ditching the liquid electrolyte, but what's the tech underneath?
Yeah, so they're relying on two specific chemical components to hit that 600 number. First, it's what they call an in situ polymerized solid electrolyte system.
In situ polymerized. Okay, what does that mean?
Think of it like the solid electrolyte material is basically formed or hardened in place during the final steps of putting the battery together.
Inside the battery itself.
Yes. And that's apparently crucial for getting maximum contact between all the layers, which you need in a solid-state design.
Okay, that's one part.
Second part, this electrolyte is paired with a lithium-rich manganese cathode material. And that's designed specifically to hold much more energy than the typical cathode materials we see today.
Lithium-rich manganese, got it. Okay, moving from performance, let's talk safety. That's often pitched as the #1 advantage for solid state, right? Not just range, but stability.
Absolutely. It's a huge selling point.
So what did Chery claim their prototype survived in safety tests? Because those demos are always dramatic.
They are, and Chery put this cell through some deliberately nasty abuse tests designed to basically break it. The sources highlight two main demos.
Okay.
First, The cell resisted flames even after being physically penetrated with nails.
Nails. Okay, that's the classic test.
That's the classic, yeah. Trying to cause an internal short provoke thermal runaway. But then they also claim it resisted flames after being penetrated with power drills.
Power drills. Seriously, without catching fire or even smoking.
That's the claim. No fire, no smoke, and apparently maintained constant performance afterwards.
Wow. Okay, we have to ask though, was this like a tiny coin cell they did this to in the lab or a full-scale representative module? Because that matters.
Yeah, the sources just call it an initial module prototype, so size is a bit unclear.
Yeah.
But honestly, the significance is still there regardless of the exact size,
How so?
because it really underlines that fundamental potential advantage of solid-state batteries. What's the biggest barrier to EV adoption besides range? It's often the fear of fire.
Right, those news stories about battery fire stick in people's minds.
Exactly. Conventional lithium-ion packs use flammable liquid electrolytes.
Yeah.
If that structure gets compromised, say, in a bad crash, or even a manufacturing defect that causes a short circuit that liquid can ignite, and you get that catastrophic thermal runaway.
So what for safety is, by swapping the liquid for a solid polymer or maybe a ceramic, you just inherently remove the flammable stuff, making the vehicle safer by design.
Precisely. That inherent stability, that's the game changer. Not just for performance, maybe allowing different pack designs, but for consumer trust. And maybe enabling designs that don't need these massive, heavy cooling systems and safety casings you see now.
Right, potentially lighter cars, too, then. Okay, now we get to the part that always triggers the most scrutiny. The road to production.
The reality check.
Chery isn't just showing off a cool science project here. They've laid out a stunningly bold projection for getting this to market. What's their timeline?
They've announced a remarkably fast two-part plan. First, they're aiming for pilot operations, getting the first batteries out of a pilot plant in 2026.
2026 for pilot. Okay.
Then, the really aggressive target, broader commercial application, mass rollout, set for 2027.
2027. Wow, that is fundamentally disruptive if they hit it. The key insight here seems to be Chery is trying to shift the whole global EV race away from just making current liquid batteries a bit better.
Incremental gains, yeah.
Yeah, to forcing a jump to a totally new technology. They're making the world bet on a new chemistry, not just slightly better engineering of the old one.
They absolutely are. I mean, if Chery actually meets this timeline, they would leapfrog potentially years ahead of many international competitors. Lots of folks still expect solid state maybe 2028, maybe even 2030 at the earliest.
And even their domestic rivals, like BYD, CATL.
It puts huge pressure on them, too.
Yeah.
They're also targeting solid state production, but more like small-scale stuff around 2027. Chery's talking broader commercial application then. And this comes right after Toyota accelerated their solid state plans, too. It shows the race is really heating up globally, specifically on solid state now.
And this isn't just a side project for Chery, right? It's backed by serious money.
No, not at all. Chery specifically earmarked 25%, a quarter of the funds from its big Hong Kong IPO for next-gen tech like this solid-state project.
A quarter of the IPO funds, that's commitment.
It is, and the potential prize, it's enormous. EV Tank, an analyst group, projects that worldwide solid-state battery shipments could hit 614 GWh by 2030. That's over 10% of the total projected battery output then. And a market size maybe over 250 billion yuan, what's that, about 34 billion US dollars. Being first, or among the first, in that market. That's the ultimate strategic win.
Huge stakes.
Huge. Now, as incredible as those claims and timelines sound, this is where we have to pump the brakes a bit and inject, serious dose of reality.
Okay, here comes the skepticism.
Well, yeah. The road from a 600 Warrage clay drab sample to full-blown automotive-grade mass manufacturing, history tells us that road is long, and it's paved with setbacks.
Right, this is the nuclear fusion parallel people always draw, the always 5 years away technology. We've definitely seen companies overpromise on solid state before. What specific hurdles beyond just hitting 600 Warrage creatures should make us pause?
Well, we've seen previous attempts, even from companies associated with Chery, where the initial targets had to be walked back quite dramatically.
Like what?
Like maybe they aimed for 400 wage carries initially in the lab, but then production reality forced them to launch at maybe 280 wage carries, which,
is basically what high-end liquid lithium-ion batteries offer today.
Exactly. So that kind of scaling back shows just how immense the difficulty is in replicating that lab success cheaply, consistently, and at massive scale.
Okay, let's break down those difficulties, because they sound pretty technical. You mentioned cost, maybe 2.8 times higher?
Yeah, estimates put current solid-state costs at potentially 2.8 times higher than liquid packs, mainly due to costly materials like sulfides and really low production yields right now. Making them perfectly is hard.
Okay, cost and yield. What about the engineering challenges? You mentioned high pressure and something called interfacial impedance. What's the pressure issue? Does it need high pressure during manufacturing or when it's running in the car?
It's during operation, and that's a huge headache
Why?
because you've got a solid inside the battery, the electrolyte touching the electrodes. To make sure they stay in perfect conductive contact, you need to apply constant high pressure compression, basically.
Okay.
If that pressure drops even a little, the connection weakens and the battery's efficiency just tanks.
So what does that mean for the battery pack?
It means the usual flexible or sort of semi-rigid battery casings we use for liquid-ion batteries. That probably won't work. The final pack has to be physically heavier, much more rigid, and needs specialized, likely expensive casing just to maintain that constant high internal pressure.
Ah, so the amazing energy density gain you get from the chemistry might be partly eaten up by the weight of the super strong, rigid casing needed to keep the pressure up?
That's the potential trade-off, exactly. It's a tough
Ah,
engineering problem.
brutal. Okay, and the other term, high interfacial impedance. What does that mean for me, the driver? If my battery has high interfacial impedance, so what?
It's basically like high internal resistance or friction right at that surface where the solid electrolyte meets the solid electrode.
Okay, friction.
And when that impedance, that resistance is high, moving charge across that boundary is slow and inefficient. That's terrible news for two things drivers really care about: fast charging speed
Right, nobody wants slow charging.
and rapid power delivery for acceleration. You floor it, you want the power now. High impedance makes that sluggish. So Chery has to prove they've solved this, that their solid electrolyte can conduct electricity quickly enough for real-world driving.
It really sounds like the core engineering challenge is just making a solid conduct electricity as well, as easily as a liquid does.
That's a huge part of it, yes.
Right.
It's fundamentally harder. However, we can't just look at this high-end solid-state chase in isolation.
What do you mean?
While the industry, especially in China, is pushing hard on these super high-density, potentially super expensive solid-state batteries, they're also moving incredibly fast on the other end of the spectrum.
Ah, you're talking about sodium-ion batteries.
Exactly. We're seeing this concurrent rise of sodium-ion chemistry being produced, like right now in China.
And those are
Significantly less energy dense. You're definitely not hitting 1,300 kilometers with sodium-ion, but, and this is the key, they are dramatically cheaper.
cheaper because sodium is more abundant than lithium.
Abundant and easier to process. And they're inherently safer too, generally speaking, because they don't rely on some of the more volatile material. So it shows this kind of strategic split in the market, maybe.
How so?
The industry is trying to solve the problem of ultimate range with solid state, while also solving the problem of ultimate affordability with sodium ion. Two different approaches for different market segments.
Interesting. But we can't just dismiss this solid state effort from Chery as just, an engineering curiosity,
Yeah.
especially given the huge government backing in China, right? This isn't just a few scientists tinkering.
That's the critical counterweight to all the skepticism.
Yeah.
You're absolutely right. China has this massive unified industrial push to make technologies like solid state happen. We're talking about a 6 billion RMB major R&D initiative launched just this year, 2024.
6 billion RMB.
And explicit government policies prioritizing the supply chains, the non-ferrous metals needed as raw materials. When you combine these technical milestones, like Chery's 600 ways K-Drime, with that level of centralized state backing and strategic industrial intent, well, sometimes the traditional timelines for getting things done can compress dramatically.
Okay, let's try and bring this all together then. This deep dive, it reveals Chery has definitely hit a headline-grabbing energy density number, 600 weight kg. They've backed it up with some impressive safety claims, maybe eating more detail, but impressive. And it's all wrapped up in this industry-disrupting timeline aiming for 2027 rollout.
That's the picture they painted.
But the central conflict, the big question mark, remains. Can a cost potentially 2.8 times higher right now, and all that inherent engineering complexity, managing the pressure, the impedance, can that actually be overcome at mass scale by that deadline?
That is the multi-billion-dollar question,
Okay.
absolutely. And maybe just to leave you with a final point to think about.
Okay.
Given that high initial cost, will these first-generation 600 weight carries solid-state batteries really only be viable for the absolute top end, like ultra-luxury cars, maybe heavy-duty commercial trucks where weight savings are critical.
Or even other applications.
Maybe, perhaps drones, light aircraft, things where cost is less sensitive than performance. Could it be that the mass market, the everyday passenger car, might stick with incremental improvements in lithium-ion and maybe those cheaper sodium-ion batteries for the next few years?
So a split market. High-end gets the fancy new tech first while the rest focuses on cost.
It's a possibility we need to watch very closely, that kind of split market development.
That's a fascinating thought. Well, the next few years are certainly going to tell us whether Chery and others can actually make that huge leap from a lab sample to mass production without hitting those infamous setbacks.
Time will tell. It always does with batteries.
Indeed. Well, thank you for joining us on this deep dive into the battery breakthroughs potentially coming out of Woohoo. And a big thank you to you, our listeners, for spending your time with us today as we worked through this pretty complex but exciting material with hopefully some clarity.
Thanks for tuning in.